Alrighty, so we are back in the new year and we are covering cellular metabolism, which is one of my absolutely favorite topics. Absolute favorite topics. Starting off the new year with that grammar. So we are going to be talking a little bit about how our cells produce energy, how our bodies grow. This is going to be just kind of a big general overview for metabolism. We're not going to get too specific about things today, but really I do want to kind of introduce some I want to introduce some terminology and concepts that we're going to be covering over the rest of this class. So when it comes to physiology, that is the study of how our body operates. Like when you're in school, you probably took an anatomy and physiology class, right? Anatomy is the study of what stuff is. Physiology is the study of what stuff does. So I could label all day, this is a cell and this is the cell wall, and I could label out the mitochondria and the nucleus and talk all about like, these are all the pieces, right? Or I could say, hey, this is, if you look at your bones here, you get your radius and your ulna, right? And I could break that down for you. That's the study of what stuff is. That's your anatomy. But talking about your radius and ulna, what's really cool about them is if I spin like this, if I do what's called supination, if I do what's called pronation, they actually cross over one another like this. They do this really cool little spinning action. And that spinning action is what they do, right? That pronation, that supination, pronation is what we call that, right? That's almost like the physiology. Technically, that's studying body movements. We actually call that kinesiology, but kinesiology is the study of how our body moves. And those are really the three things you need in order to become a really good personal trainer and understand why it should be 12 reps instead of 5, or why it should be running, at 65% of your heart rate instead of 85% of your heart rate. All of that has to do with our understanding of physiology, kinesiology, and anatomy. So we are going to be studying a lot of physiology. We're going to talk about like what your cells are, but mostly what we're going to be spending our time is understanding how they function. So our objectives today are to understand metabolism, and the two components that make up metabolism, which we call catabolism and anabolism. Understand what takes place in, this is always fun to say, what is called an oxidation reduction reaction. We're not going to call it that when we get there because that's hard to say, but we'll talk about it. Understand cellular respiration just a little bit. Cellular respiration is how your cells take in ingredients and spit out energy. And it's one of my favorite things to talk about. It is basically the main object of this entire 12-day class. We really want you guys to understand cellular respiration really clearly. So we will talk a little about glycolysis and aerobic metabolism and our different energy pathways. So chemical reactions are taking place in your body at all times. They are responsible for literally everything that you do, which is pretty freaking cool. All these really cool little molecules that are interacting with one another and creating these really cool little explosions and bonds and all kinds of really neat stuff that basically allow you to function. Your thoughts, for instance, are little electrochemical signals that start in your brain and then they travel around to wherever it is they're going. Oh, we lost Chris. Those are, how do we create those little electrical, impulses? Well, we use what are called electrolytes. You guys are probably familiar with electrolytes if you've ever had a Gatorade or a Smart Water or anything like that. And what electrolytes are is they are sodium and potassium. Those are the big ones. If you've ever eaten put salt on your food, or if you've ever, eaten a banana, the reason you'd eat those things is because they are really rich and full of electrolytes. And when you put sodium over here and you put potassium over here, and then if you flip them and then allow nature to flip them back, and then you flip them again and then nature flips them back, this creates electricity. It's kind of like static electricity. You know, when you rub your socks on the carpet and then you go over and, you know, zap your mom. That's what I used to do all the time. I used to drive her crazy. You know, that's a static charge, right? You created a little bit of electricity by rubbing things back and forth. Well, sodium and potassium, when they rub back and forth like this, they create an electric charge. And every time you create a little thought, or every time you want to move something, your brain creates a little electric charge, and it goes from here to here to here to here to here, and it travels down your spine and then over here, and then eventually it zaps your bicep, and your bicep does that. Crazy, right? So obviously that takes a lot of energy. You know, moving all those sodium and potassium ions, just flipping them back and forth like that, doing all that takes a lot of energy. So we need to be able to produce energy, and we're going to do that by breaking down food. So food is going to come in the form of things like glucose, protein, fats, right? Those are our three nutrients: proteins, fats, and carbs, right? And we're going to take those things and we're going to break it. You know, they're so complicated. Like a protein is this big long chain of what we call amino acids. Carbohydrates, these big long chains of sugars. Fats, these big long chains of little fatty acids, right? And what we're going to do is we're going to use our digestive system to break all that down into individual ingredients, right? Carbohydrates, bread, right? Vegetables, fruits. They're going to come from these big long chains, and we're going to break those chains up until we're left with individual single sugar molecules. And those single sugar molecules are going to go into our cells, and our cells are going to use oxygen, and they're going to use enzymes, and all these cool little things are going to happen, and it's going to spit out energy. And then our energy is, we're going to use that energy to move those sodium and potassium ions and create a little bit of electricity. And it's all because of chemistry. And that is metabolism in, I don't know, 60 seconds. Let's spend more than 60 seconds, shall we? So chemical reactions are going to involve your metabolism by breaking down nutrients. You have got 6 essential nutrients here in the universe, right, that we use. I'm sure out there there's somebody using something else, but the 6 that we use are proteins, fats, carbs, vitamins, minerals, and the most important of all, water. Those are our 6 essential nutrients. You need to have a steady supply of all of those ingredients coming into your body, and you need to constantly break them down in order to build them back up into U-shaped stuff. You know, like a lot of people think like, you know, how many bodybuilders have you guys known who are like, I need more protein. I'm working out like crazy. I got to eat protein. You know, it's like, look, here's the thing. Yes, you need enough protein, but I do think that bodybuilders sometimes go crazy on the protein. And it's like your body, if you eat too much protein, you know what your body does? It actually turns into carbohydrates. It's like, I don't need that much protein, and it turns it into carbs. And, you know, I'm not a vegetarian, but is anybody in here a vegetarian? Don't got any veggies? No? Okay, well, you know, if you are a vegetarian, you know, a lot of people think it's like, oh, if you're a vegetarian, how do you get enough protein? It's like, first off, there's a lot of protein in vegetables and beans and all kinds of plant matter. Tons of protein out there in that stuff. You know, you don't have to eat. Like, people sometimes think the way metabolism works is like, it's like your body gets like, you're eating like a chicken breast or something, and your body goes, oh, we did push-ups today. That's perfect. Put that right here. And all of a sudden you get like chicken breast for your breast. No, that is not how that works. Luckily, you know. But what your body will do is it'll take that chicken breast and it'll break it down into these 20 ingredients that we call an amino acid. 20 different amino acids. And then it will reassemble them in U-shaped stuff. And now all of us have slightly different proteins, you know. Alexia, you're the only one with your camera on right now. So I'm going to use you as my example, but you've got brown eyes and I've got blue eyes, right?
Yeah.
So you've actually got an extra protein in your eyeballs that I don't have. I am missing one of those proteins. It's called melanin, right?
Uh-huh.
And so that's actually giving you an eye color. Mine is actually, blue eyes are actually a lack of eye color. In fact, you actually do have blue underneath, and it's actually just brown on top.
I messed with my mom. I said, Mom, the light is affecting my eyes, my blue, beautiful eyes. I told my mom started laughing.
Yeah. So that's actually a protein. So, you know, the shape of that protein in your eyeball is just a slightly different than the ones in mine, right? And that's what makes the difference between all of us, these little tiny differences. You know, it's all the same ingredients for all of us. Our DNA is so similar, you know, but those little tiny differences, you know, putting something in this order instead of that order, you know, instead of like, you know, the alphabet, we lay it out, what, A, B, C, D, E, F, G, right? Imagine if I laid my alphabet, instead of A, B, C, D, E, F, G, I was like A, C, B, and then the rest of it was all the same. That little tiny difference is what gives somebody blonde hair and gives somebody else brown hair, you know? So it makes my hair curly. I don't know, maybe it's what's making my hair fall out. But everybody's got just slightly different shapes to all their proteins. And that is what your metabolism is responsible for. You've got all these cool different proteins. You've got all these cool ways that you're going to use carbohydrates and fats. Those are what we call macronutrients. And we call them macro because macro means big, right? So you need lots of macronutrients every day, but you also need vitamins and minerals. Some of your body isn't even organic. Some of your body is rocks. And I mean that. Your skeleton, right?
You're right.
It's made of calcium, right? And phosphorus. Well, calcium and phosphorus, you ever look at those in nature? This is what calcium looks like. It's a metal. It's a freaking rock, you know? It doesn't look like that in our body because it's combined with phosphorus. And so we have what's called, and if you look at phosphorus, by the way, which, by the way, is what they use in fireworks, phosphorus looks like this. So you take those two metals and you put them together and you end up with what's called calcium phosphate. And that looks like this. And that's what makes up your bones. So inorganic materials, friggin' metals, rocks, things like that. You need those. Sodium, potassium, right? You know, sodium is an element, looks like this. And potassium as an, well, actually not that, that's the wrong page. It looks like this. That's sodium. And then you've got chlorine. Chloride looks like this. If I can find a picture.
Soil.
Come on. There we go. Kind of looks like that. And if you put sodium and chloride together, you know what that looks like? Table salt.
Oh my God.
So that is sort of the inorganic stuff. So you've got proteins, fats, carbs, minerals, which is rocks and metals and things like that that we need for our body, copper, manganese, molybdenum, which is my favorite to say. And then you've got vitamins as well. And vitamins are kind of like proteins. They're like really small proteins. They look similar to proteins. They don't actually have any energy in them because they're so small. But vitamins act as what we call an enzyme. And an enzyme is what we're going to talk about today. Enzymes are basically like little proteins that are required for metabolism. They kick off chemical reactions. How the heck do you get sodium and potassium, to come? Oh, well, sorry, sodium and chlorine, right? That's the sodium chloride. That's table salt. How the heck did you get those to come together? Well, a lot of times in our body, we need enzymes to make that take place. I always tell people enzymes, they're actually proteins. They don't really have any energy of their own, but they kick off the use of energy. It's kind of like the key to your car, right? Your car runs on gasoline. But it doesn't ever use any of that gasoline until you stick the key in the ignition. That's kind of like what an enzyme is. It doesn't have any energy of its own, but it's what starts the chemical reactions. So you've got all millions of enzymes in your body that are making all these chemical reactions take place. And lastly, we've got water, which is the most important element because it's mostly made up of hydrogen. And hydrogen, if you look at the periodic table, is the very first element.
Oxygen.
number 1. Oxygen's up there as well, but that is actually number 8.
It's hydrogen.
Yep. So hydrogen's number 1 right here. And that is actually really important. It was the very first element in our universe. And eventually we also ended up with oxygen.
Yeah.
And when you put those two things together, you end up with what's called, when you have 2 parts hydrogen and 1 part oxygen, you end up with what's called H2O.
Yes.
And that is what breaks up all these chemicals. How do you take, when you put salt in water, it dissolves, right? Disappears.
Yeah.
It's separating the sodium and the chlorine, which is why they use salt if you have a pool. They say your pool's got chlorine in it, and it does, kills bacteria and stuff. But they use salt in order to make that happen, which is why it messes up your hands. If you spend too much time in the pool. So that's water. Water is the most important element we've got on this planet, So that is sort of a brief overview. So let's go ahead and get some definitions up here. Let's start talking about how this is all relevant to us, because you guys just got slapped in the face with a bunch of chemistry. Let's get into the stuff that's relevant.
Good morning.
So metabolism by definition. Oh, what's that, Alexia?
My son, 1 second.
Oh.
I'm gonna mute myself.
No problem. Yeah, that's actually great. So let's go ahead and define what metabolism is, because I've been talking about metabolism all morning, right? Well, metabolism is going to be defined as any and all chemical reactions taking place inside the body. So when you scratch your skin, right, and you leave a mark on your skin, and then your body's going to come along and repair all that, it's part of your metabolism. When you take in a donut and your body breaks it down into a bunch of sugar, and then you're like, because you got a sugar rush, that's part of your metabolism. When your brain makes a thought, that's part of your metabolism. Any and all chemical reactions. If it is a chemical reaction taking place in your body, it's part of your metabolism. It's kind of fun. Your spit has a bunch of enzymes in it. It's called salivary amylase. We'll be talking about it tomorrow. And when you take, let's say, bread, right? Bread's a really good example because it breaks down really easily. You take a little piece of bread, stick it under your tongue. What's going to happen? It's going to dissolve, right? Why did it dissolve? Well, the enzymes in your saliva are breaking up that bread into individual little sugar molecules. That is a chemical reaction. That's part of your metabolism. Everybody's metabolism is a little bit different, right? But by definition, it is any and all chemical reactions taking place in the body. Now, I talked about repairing your skin. How do you repair your skin? You make new skin. Well, how did you break down that bread? You took this big complicated thing, you broke it down into individual glucose molecules. So metabolism goes in 2 directions. It either goes this way or it goes that way. It never goes this way or this way. It can do 2 things. We're going to break it down into 2. You either have metabolic reactions that build stuff up, or you have metabolic reactions that tear stuff down. Those are the 2 divisions of metabolism. So first one is what we call anabolism. You might have heard of the term anabolic, right? You'll hear bodybuilders say this all the time. They're like, you got to stay anabolic. And what they mean by that is like, you got to eat. Anabolism is the building up of stuff, okay? It's taking something really simple and building it up with other simple stuff to make something really complicated. Picture yourself building like a shed in your backyard or something like that, right? So let's say you go to the hardware store, you get a bunch of pieces of wood, you get a bunch of nails, some wood glue, all these materials, you take them back to your house and you start taking them, right? The nails are their own very simple thing. The piece of wood is its own very simple thing. But when you start adding them all together, right? And you take that piece of wood and you add it to that piece of wood, and you take that piece of wood and you add to that one, and you build them all up. You end up with this big complicated shed in the end, right? That's an anabolic reaction. So using an example, it's relevant to us as personal trainers. Let's say you take a chicken breast and it's been broken down into all these little individual components. And then you went to the gym and you did a bunch of bench presses, right? Or shoulder presses or something. You did, it was leg day. You did some squats, right? Well, what just happened is you just broke down all your muscle. You tore up all your muscle. You damaged it like crazy. So what your body's going to do is your body's going to go, what did you do? You broke everything. I got to fix all this, right? So it needs to build up some new muscle. So what it's going to do is it's going to take the ingredients from that chicken breast, and it's going to add them all together into new little proteins, and it's going to repair your muscles. But instead of repairing them back to where it was, it's actually going to repair them just a little bit more resistant to damage in the future, right? Like your body's going, well, if you're going to keep breaking all this crap, I'm going to make it more resistant to breaking, like, so you can't break it anymore. And then your muscles get a little bit bigger, a little bit stronger. And that's how we grow. Through little breakdowns. So the building up of making new muscle is what we call anabolism. It's an anabolic reaction. Now, obviously, we needed to get the ingredients in order to do that, and that's where our catabolic reactions come in. Catabolism is the breaking down of complex molecules to form simpler, smaller molecules. So, for instance, taking that chicken breast and breaking it down into individual amino acids. That is a catabolic reaction. When you take bread and you put it in your spit and it starts breaking down, that is a catabolic reaction. Anabolic reactions build stuff up. Catabolic reactions break stuff down, which is why you will often hear this phrase when you're talking about metabolism. You'll hear people say, catabolism fuels anabolism. You take a donut, you break it down catabolically. Then you get to use all that sugar to anabolically give yourself the energy to do some squats. For the record, donuts are not your pre-workout meal. If Eddie were here right now, he would be disagreeing with me.
I've done it before.
What's that, Edwin?
I say I've done it before.
Yeah, we all have.
I'm like, oh, sugar. I'm sugar. It makes sense. Energy. Let's go.
Yeah. See, I used to work out with my students in class. When we were in person, I worked out with my students all the time in class because it was part of class. But Mo's class is the practicum section. So they were in the gym, for 5 straight, it was like in the gym the whole time. Mo had a steady supply of donuts in his class. True story. So catabolism fuels anabolism. We break stuff down with our digestive system. We build stuff up with our metabolism later. So just to kind of show you a brief video of that.
Connection to the natural world and a research.
That's the right video. Yeah. All right. So here's a really brief overview of everything we're going to be talking about today. I'm going to minimize myself here, and I will be back in a moment, but I'm going to leave you in the capable hands of Mr. Hank Green.
I weigh about 80 kilograms. Most of that, let's say 64%, is water, though you can't tell by looking. I mean, as organisms go, I like to think that I look fairly solid. After water, the next largest proportion of me is protein, about 16%. Not just in my muscles, but also in things like the tiny sodium-potassium pumps in my neurons, and the hemoglobin in my blood, and the enzymes driving the chemical reactions in every one of my 37 trillion cells. And another 16% of me is fat, which I'm totally okay with. 4% of me is minerals, like the calcium and phosphorus in my bones and the iron in my blood, and 1% is carbohydrates, most of which is either being consumed as I talk to you or is sitting around as glycogen waiting to be used. But here's the thing, it's not like I just ate 80 kilograms of food and then all this happened. Instead, my body, like yours, is constantly acquiring stuff, extracting some of it to keep, burning some of it for energy, and getting rid of the rest. But even the stuff that my body does hold on to doesn't last forever. Some of the chemicals that I absorb in my food eventually become a part of me, but enzymes wear out and membranes break down and DNA DNA gets oxidized, so they get discarded. And then I need more of those chemicals to reconstruct the material that I've lost. As a result, over the course of my lifetime, my cells will synthesize somewhere between 225 and 450 kilograms of protein. That's like 3 or 4 or 5 separate me's just made of protein. And all the protein and fat and carbohydrates and nucleic acids that make up me, of course, come from food. Every organism has to keep taking in and breaking down food to keep resupplying itself with the raw materials it needs to survive. And all that activity requires energy, which we also gain from food. So how do our bodies actually convert what we eat into energy and raw materials? The answer is a never-ending series of reactions that are dedicated to doing two vital and totally contradictory things. One set of chemical reactions destroys the reactants that you give them, reducing big, complex substances into molecular rubble, and the other set reassembles that rubble into new and bigger products that are put together again to make you. So our bodies are constantly reinventing themselves in a perpetual state of loss, but also always rebuilding. And even though all of this is happening at the cellular level, its consequences could hardly be larger. These two sets of reactions are where everything that we've learned so far about the digestive, endocrine, circulatory, and respiratory systems really starts to come together. Together, these processes make up your metabolism. Now, the sciencey word metabolism has come to have a meaning in popular speech, but metabolism isn't just one thing. People talk about metabolism as meaning like how fast your body burns the fuel in your food or how high your personal energy level is, and that's fine for use by personal trainers and fitness magazines. But physiologically, metabolism really describes every single biochemical reaction that goes on in your body. And maybe more importantly, it reconciles two conflicting chemical processes that are always simultaneously underway inside of you. One of those chemical forces is anabolism. Anabolic reactions construct things and consume energy. These are the processes that take the small monomer building blocks in your food, like monosaccharides and fatty and amino acids, and build them into bigger, more complex polymers like carbs and fats and proteins that are used in your cells. Then, when you need new building blocks or you need to release some energy, those polymers in your body, or new ones in your food, get broken up by catabolic reactions. The processes of catabolism break down bigger molecules, and in breaking their bonds, release the energy you need to stay warm and move around and provide your cells with fuel to build those polymers back up again. To be honest, your metabolism is a lot like Sisyphus. It works really hard, but it is never finished. And the boulder that your inner Sisyphus is always pushing uphill and watching fall back down, that's nutrients, the molecules that your body is forever breaking up and then rebuilding only to have them break apart again. And these nutrients, the materials that your body needs to build, maintain, and repair itself, come in 6 major groups. By volume, the majority of what we consume and what makes up our bodies is water, so that's maybe the most vital nutrient. Then there are vitamins, compounds that come in either fat-soluble or water-soluble forms. They aren't used as building blocks or for energy, but they're essential in helping the body make use of other nutrients that do those things. Vitamin C, for example, helps improve iron absorption, while vitamin K is crucial to blood clotting, and some B vitamins are important in the production of ATP from glucose. Minerals, like vitamins, don't provide fuel, but they have all sorts of other functions. Calcium, magnesium, and phosphorus harden bones and teeth, while iron is of course crucial in hemoglobin. Plus, potassium, sodium, and chlorine help maintain your body's pH balance and are used in action potentials. So water, vitamins, and minerals are all necessary. But the 3 major nutrients that everyone always talks about, the ones you find on food labels from oatmeal to Pop-Tarts, are carbohydrates, lipids, and proteins. Most of the carbohydrates you've ever eaten, with the exception of lactose in milk, originally came from plants. Mono and disaccharides come from fruits, honey, sugar beets, and sugarcane, while polysaccharide starches come from veggies and grains. The main thing you need to know is that the monosaccharide glucose is the be-all, end-all molecular fuel that your cells need to make ATP. ATP being the molecule that your cells use to drive anabolic reactions when they need to make new polymers or get anything else done, whether that's operating a sodium-potassium pump or detaching the head of a myosin filament to contract a muscle. But ATP is too unstable to store, so cells often store energy in the form of glucose, which they can then catabolize and convert to ATP when they need it. Now, some of your cells can get their energy from fats, but many of the most important ones, like your neurons and red blood cells, feed exclusively on glucose, so most of the carbs that your intestines absorb are converted to glucose for that reason. But if it's not needed right away, that energy can also get stored as glycogen in your liver and muscles, or converted to glycerol and fatty acids to make triglyceride fats. And even though there seems to be some kind of marketing war going on against dietary fats, we most definitely need them. The fats in your adipose tissue store energy, of course, but they also store fat-soluble vitamins and cushion your organs. Lipids also form the myelin that insulates the neurons in your brain and throughout your body, as well as the oil in your skin, and they provide the vital calorie content found in breast milk. But there are other important lipids like cholesterol, which is the precursor to things like testosterone and estrogen, and of course phospholipids, which form the cell membrane in every single one of the 36 or so trillion cells you have. Now, if you're into eating meat, a lot of the fat you ingest might come from that, but guess what? Plants have fat too. Plants use lipids for energy storage just like we do, except they do it in fruits and nuts and seeds, which, when you think of it, are kind of like plant breast milk. It's food for their growing babies. Either way though, when you eat lipids, your body breaks down triglycerides into glycerol and fatty acids. Those molecules can then be processed and used in the making of ATP, or they might be converted into other kinds of fatty acids, which your cells can then reassemble into your very own triglycerides or phospholipids. And your liver happens to be great at converting one fatty acid into another, but there are some it just can't synthesize. For example, omega-6 and 3 fatty acids are called essential fatty acids because your body can't make them, so they have to be ingested. They get turned into all kinds of useful molecules like the ones used for synapse formation in the brain and for signaling inflammation during the healing process. But if carbohydrates provide energy and fats insulate and store energy, then just about everything else is done with proteins. They form the bulk of your muscle and connective tissue, but they're also what the ion channels and pumps are made of in your neurons and muscle cells, and they make up your enzymes, which are responsible for pretty much every chemical reaction in your body. In other words, your body runs on protein, and pretty much is protein. Nutritionally speaking, meats, dairy products, eggs, legumes, nuts, cereals are all particularly high in protein. But because everything we eat was once alive and every cell of every living thing contains protein, as long as you're eating whole foods, you're at least partially restocking your protein supplies. That might seem like you'd have to eat muscle to make muscle or eat enzymes to make enzymes, but that's not how it works. Since all your proteins are made up of just 20 amino acids, the differences between the thousands of unique proteins are simply in the sequence of those amino acids. And of course, you have a specialized molecule that knows just which amino acids to put together in what order to make a certain protein. It's called DNA. When you consume some hamburger, for example, the protein actin in the meat gets catabolized into its component amino acids, which gets mixed up with all of the amino acids from all the other proteins in the meat, like the collagen and elastin and titin and myosin, as well as all of the proteins from the bun and the tomato and the mayonnaise. Those amino acids then get reassembled using anabolic reactions into your very own but somewhat different proteins as defined by your DNA. Each cell is like a picky little Gordon Ramsay, and it has to have every amino acid needed, every ingredient present, before it will even think about starting to make a protein. And just like with your lipids, your cells can improvise and convert some amino acids into others if they're missing an ingredient. However, there are 9 essential amino acids that you cannot make from others and have to eat. Now, lots of foods don't provide every essential amino acid, but when you combine foods like beans and rice or pasta and cheese, you do get all of the essential amino acids, which is important because, remember, after water, you are mostly made of protein, on the order of 16%. But what about the 1% of you, the carbohydrates? How that tiniest fraction of you ends up creating all of the energy is what we'll discover next time. But for now, you've learned all about the vital nutrients, including water, vitamins, minerals, carbs, fats, and proteins, as well as how anabolic reactions build structures and require energy, while catabolic reactions tear things apart and release energy. And together, these competing forces form the wonderfully conflicted process known as metabolism. Thank you to our headmaster of learning, Linnea Boyev, and thanks to all of our Patreon patrons whose monthly contributions help make Crash Course possible, not only for themselves, but for everyone everywhere. If you like Crash Course and want to help us keep making videos like this, you can go to patreon.com/crashcourse. This episode was filmed in the Dr. Cheryl C. Kinney Crash Course studio. It was written by Kathleen Yale, edited by Blake DiPestino, and her consultant is Dr. Brandon Jackson. It was directed by Nicholas Jenkins, edited by Nicole Sweeney. Our sound designer is Michael Aranda, and the graphics team is Thought Cafe.
Okay.
My whole production.
What's that?
I said the whole production right there, the credits at the end. Nice.
Yeah, it's a lot. I try to always like make sure that I play the credits whenever I'm like.
Yeah, to get credit. Yeah, for sure.
Yeah, we're gonna be watching a lot of Crash Course videos in this course. Mostly because I think sometimes the stuff we're talking about is pretty abstract. So when you get to watch those animations, it really helps you understand how stuff works.
Yeah, pretty interesting. I eat a lot of those pollo loco like double chicken bowls, you know. So he's like, oh, if you mix rice and beans and cheese, so that rice, beans, chicken, cheese.
Yep.
A buttload of sodium probably.
Oh, sure.
Yeah.
That's why you make sure you work out hard enough to sweat it all out.
Yeah.
These videos are available on Canvas, right?
My videos are, and then obviously you could watch that section again. But that is a crash course video. If you literally just go to YouTube and you look up crash course metabolism, it will be this video right here.
Nice. Thank you.
Yeah, no problem. They literally have it's an entire physiology course on their website. It's all for free. It's all on YouTube. I am obsessed with these two guys. The guys who started this is that guy, his name's Hank, and his brother John. I've been watching them on YouTube literally since 2007. Did you guys ever see the movie The Fault in Our Stars? This one here.
Yeah.
This movie, or if you've ever seen the book, this book here, was written by that guy's brother. Anyway, all right, let's go ahead and talk about how this actually happens. So, like I said, metabolism is going to be made of anabolic and catabolic reactions, right? Anabolic stuff builds stuff up. Catabolic stuff breaks stuff down. So it goes from simple to complex, that's anabolic. If it goes from complex to simple, that's catabolic. So how the heck do we actually get that to happen? Well, one of the ways that our body actually anabolically builds stuff up is, remember earlier I said water is the most essential nutrient, the most important thing ever, right? That is because we actually use water to break stuff down, and we actually take water out in order to build stuff up. We actually use water in order to do this, or rather we use the ingredients associated with water. So the first thing we need to look at when we look at building stuff up, when we're talking about anabolism, anabolic reactions, we're going to be talking about dehydration synthesis. So let's break, if we just break those words down, whenever you hear the word synthesize, it means to make something, right? You take milk, you take chocolate milk powder, you put that chocolate milk powder in the milk, you stir it up, you have synthesized chocolate milk. It's magic. My parents love chocolate milk, and I had a lot while I was home for Christmas. Not good for you. But synthesizing means to make stuff, right? You're synthesizing something. They synthesized a COVID vaccine last year, right? Dehydration means to take the water out of something. Okay. So when we're linking molecules together, one of the ways that we're going to do that is through dehydration synthesis. So I'm going to go ahead and take a copy of this here, and show you how this works. So take a look over here. You can see we've got two molecules, right? These are actually two molecules. This is actually two sugar molecules right here. And you'll notice they're bound together, actually. If you look, you see how you can see here, they're actually linked together. There's this little link right here holding the two of them together. So this is an individual sugar molecule, and this is an identical individual sugar molecule. And we wanted to link these two sugar molecules together. So we took something that was very simple, two things that are very simple, right? One simple sugar, and we put them together. We linked them together. That is an anabolic reaction. How did we do that? Well, take a look right here at this individual sugar molecules. You notice how there's this little hydrogen ion right here on the end. And then over here, there's another one, and a little bit of oxygen, right? So there's a little bit of H, there's an H here, and there's another H here. Now, if I were to take those things away, right? If I literally just go like this and I drag this out of here, well, now I have taken a hydrogen molecule, I've taken another hydrogen molecule, and I've taken an oxygen molecule, and I pulled it away. Well, that's H plus O, more commonly known as H2, because there's two H's, O. That's water. I pulled the water, a little bit of water off of this one and a little bit of water off of this one. Now what's going to happen is nature is going to go, well, this is an unhappy molecule and this is an unhappy molecule. So what it'll do is if I've got that H2O over here now, it's left with this random oxygen molecule. And that random oxygen molecule is actually what's going to link these two together. They're going to share this. You know, it's like they're trying to fight over this oxygen molecule, right? He's grabbing this side, he's grabbing this side, and they're both held together. And now they're linked, right? In sort of a tug of war. And so now we've got a double sugar molecule that's linked together. If you do this enough times and you link enough sugar molecules together, you end up with these big, long, complex chains of sugars. And that's what we call carbohydrates. Carbohydrates are these big chains of all this, where an individual sugar molecule, we suck the water out, right? So you can see, we literally grabbed this H and we put it over here. And we grab this H and we put it over here. And we grab this O and we put it over here. And we just kind of linked them all together, right? And so O plus H equals H2O. So we sucked the water. We sucked half of the water out of this one here. We sucked half the water out of this one here. And we left this guy alone. We left that oxygen molecule behind. So we dehydrated that molecule and ended up with a complex thing. Now that's dehydration synthesis. That is how your body builds stuff up. It pulls the water out of stuff. Picture going to the beach, right? You're at the beach and you go down to the sand near the water. And you've got all this sand with all this water in it, right? And you want to make a sand castle. Well, what do? You squeeze it really hard and some of the water comes dripping out the bottom. And then you're left with this hard packed sand ball. You dehydrated it. And now all that individual sand is packed together in almost what is like a rock. If you were really able to dehydrate it, it would really get stuck together eventually. And that is dehydration synthesis. That's how our body combines stuff to make stuff. We can, by the way, we can do this with proteins as well. This is a peptide bond. Proteins, you'll notice the ingredients are slightly different. Take a look here. You can see there's a lot of C's, a lot of H's, and a lot of O's, right? CHO. That's carbohydrates, that's carbon, H is hydrogen, O is oxygen. So all carbohydrates are made out of those three ingredients: carbon, hydrogen, and oxygen. For the record, proteins are actually made out of the same thing, except they have a little bit of nitrogen as well. So carbon, hydrogen, oxygen, and nitrogen. You add nitrogen and all of a sudden these things form these really cool shapes, you know? There are so many shapes that proteins can make thanks to that nitrogen. Oh, those are examples of foods. Yeah, that's kind of what I wanted, but yeah, actually, here we go. Look at all these really weird, wacky shapes that proteins can make. They can make, you know, proteins in your muscles. They can make enzymes. They can make, there's spider silk, just a freaking protein, all kinds of different types. And they just look in these really cool, interesting shapes. You know, that's all thanks to nitrogen. So what's funny about carbohydrates and proteins, they are exactly the same ingredients, plus nitrogen in the protein. For the record, fats, also the same ingredients as carbohydrates, just in a very different shape. So fats are hydrogen, carbon, and oxygen as well. And that's why if you've ever been watching a sci-fi movie and they say, oh, they're carbon-based life forms like us. You always hear them say that. It's because carbon is pretty much in everything that makes us up. It's in carbohydrates, carbon, hydrogen, oxygen. It's in fats, carbon, hydrogen, and oxygen, and it's in protein, carbon, hydrogen, oxygen, plus nitrogen. So if I want to take two amino acids and link them together, just like I linked my carbohydrates together, what do? Well, I suck the water out of it, right? So here, is an individual amino acid, right? So this is one amino acid right here, and this is another amino acid right here. And if you pull the hydrogen off, if you pull the oxygen off of this one, and you pull the hydrogen off of that one, and you pull the hydrogen off of that one, you end up with two hydrogens, H plus another H, and you end up with an oxygen plus an O, and that's our H2O. And there we go. We dehydrated it. Now we have a linked amino acid. And if I link that amino acid to another one and to another one and to another one, just like we were talking about earlier, and I put it in this order here, that's how you get blue eyes. And if you put it in that order, that's how you get brown eyes. And if you put it in that order, that's how you get DNA. You put it in this order, that's how you get bone. You put it in this order, that's how you get skin. And most importantly, you put it in this order, that's how you get muscle. So that is how we link stuff together. That is the anabolic reactions in a nutshell, okay? We use dehydration synthesis to suck the water molecules out of things, and then they get linked together. They get attracted to one another because they can fight over that oxygen molecule that we leave behind. We don't pull out HHOO, H2O2. We don't pull that out. We pull out H2O, and we leave an O behind. That way those molecules can fight over that oxygen and they can link together. Does that make sense, everybody? Cool. For the record, you're actually not going to be super tested on this, but understanding this makes it way easier to understand nutrition tomorrow. When I talk about digestion and you're like, how the heck do you take bread and turn it into goo? This is how. It just makes it easier to understand. So what's the reverse? What happens if we take all of this and we do it in exactly the opposite direction? What happens if instead of pulling water out of something, what if we shove water into something? Well, you know what that's going to do? That's going to break it up. Just like it's the reason why we all leave our dishes in the sink. Why do you leave? They got to soak, right? Well, you leave it in there with some water and that water breaks it all up. Here's a fun fact. You know, you think about like acid, right? You picture like, you know, Two-Face from Batman. He gets hit with the acid and it eats all his skin. You know, not in the Dark Knight one, but the comic books. You know, you think about like what acid does, right? It eats stuff away. It dissolves stuff like crazy. Well, that's what your stomach acid does. For the record, acid is really good at breaking down protein. But you know what's funny? In the universe that we live in this wonderful world that we all share, water is the #1 most dissolving substance in the entire universe. They actually call it the universal solvent. It works better than any cleaning product you've got in your kitchen. It works better than any acid you've ever seen in a movie, at least on more stuff. It may not work better on everything. You know, if I drop water on my phone here, it's not really going to do much except maybe screw up my battery if it gets in one of the small holes or something. But you know, this is plastic, right? If I drop water on plastic, it doesn't really dissolve it. Acetone, though, you drop that on plastic, it'll eat it away. Nail polish remover, it'll damage your plastic, right? That works really well. But water works better than anything else in the entire universe. It breaks down more stuff than anything else out there. And how does it do it? It does exactly the reverse of what we just talked about. Instead of pulling water out and combining stuff, water shoves itself in between and it pushes that over there and it pushes that over there. And that is what we call hydrolysis. Hydro from the word meaning water, lysis meaning a chemical reaction. So this involves the decomposition of molecules. You got something complex and you decompose it, break them up, such as carbohydrates, or maybe even fats or proteins by splitting the molecules with water. So it is exactly the same thing, but in reverse, right? So if we go back to paint here, so now let's just say I've got this amino acid over here, right? Remember, this is a linked amino acid. This is 2 amino acids attached, right? One over here and one over here. And what I want to do is I want to break them up. Well, if I got a little bit of hydrogen over here, and I got a little bit more hydrogen over here, and I got a little bit of oxygen, and I take this hydrogen molecule and I shove it right here. And then I take this hydrogen molecule and I shove it right here. And I take this oxygen molecule and I shove it right there. Well, now there's no way that they can all hold on to that grip with this little nitrogen right here. It can no longer maintain its grip with this little guy. And so it loses its grip and it gets broken apart. And now I've got an amino acid here, and I've got a separate amino acid here. It is exactly the same as dehydration synthesis, but backwards. I could do it with carbohydrates. I'm just going to put all that stuff, instead of pulling the water out, like we see here, I'm going to put the water in, right? One of the H's goes here, one of the O's goes here, and the other H goes here. And now they're separated. And that is how your body metabolically breaks stuff down and builds stuff up. Anabolically, it dehydrates things. Catabolically, it hydrates things. Catabolically breaks, anabolically builds. So that is how we use that. Now, this doesn't always happen easily. This isn't always as simple as I made it sound. Sometimes it's a little tough. You know, for instance, if you've ever tried to like scrub a pan and it had like, you cooked like hamburger meat or something like that, it's like kind of greasy. You pour water on there, you could scrub all day, it's not coming off, you know? that water and oil don't mix, water and fat don't mix very well. So what do you need? You need dish soap, right? Well, dish soap is what we call an emulsifier. When you add that in there, it breaks up all the individual fat molecules. Well, how do we do that with proteins? How do we do that with carbohydrates? Well, sometimes we use what are called enzymes. We talked about enzymes earlier, right? Enzymes are basically little proteins that coordinate chemical changes. I like to say they kick off chemical reactions. And when they actually use this, it works like they call it a lock and key mechanism. And that's why I always use the analogy of a car. Your car runs on gasoline, but you can't use that gasoline until you tell it to kick off the chemical reaction by sticking your key in the ignition. When you do that, it starts all the explosion, starts combusting, and boom, you start using your gasoline. Well, in your spit, we talked about it earlier, you've got what's called salivary amylase. It's a protein, it's an enzyme that breaks down carbohydrates. When you put like bread in water, it kind of maintains its shape fairly well. You know, it gets real soggy, and if you leave it in there long enough, eventually it'll just kind of dissolve, right? But if we want that to happen more quickly, we would add some enzymes to that water, like salivary amylase, which is why bread breaks down so much faster in your spit than it would in regular water. Fun fact, you can find videos of this online. But it's real gross looking. So enzymes basically kick off chemical reactions. And that's one of the ways that your body coordinates things. This is also a reason why you need to have protein in your diet. It's not just about repairing your muscles. It's also about, you know, keeping your metabolism healthy so that you can actually continue to break down food. One of the most dangerous things about eating disorders is that it ends up resulting in such a little amount of protein coming in that their body runs out of enzymes. And then their body, you know, when they finally do eat, it actually can't digest food. And so even eating, and this is what they call that refeeding syndrome. It's part of what we call refeeding syndrome, which is where somebody who maybe has like a really bad eating disorder and has not eaten anything in a long time, suddenly will eat a lot of food and it'll just go straight through them. because they don't have the enzymes necessary to break down that food and actually absorb it. It's pretty horrifying. Happens in majority world countries all the time. So that's what enzymes are. And that's also one of the reasons, by the way, enzymes actually live at a very narrow range of temperatures, but also, by the way. So if you've ever had a cold, you've ever had a fever, and you notice you're just like, it's like somebody's like, you got to eat something. And you're like, I don't want to eat anything. Part of that is actually also your body going, I don't have any enzymes to break it down, so I'm not hungry, which is kind of funny because your enzymes actually kind of die off when you get too hot. But that's a whole different conversation. But that's why you don't have an appetite when you're sick. So all the reason we're talking about this, the reason we're talking about all this stuff and breaking things down and building stuff up is because we in this class need to have a pretty good working understanding of chemical energy. So when we talk about doing stuff, we are talking about using energy, right? Now, what the heck is energy? Well, you know, we think of energy, it's like, I don't know, maybe like a lightning bolt. It's a good example of energy. Or maybe like a fire, you know, like flames and all this combustion and stuff. That's a lot of energy being released. Gasoline, you know, if you've ever or setting off a firework, you know, it's a tons of energy is released. Well, energy is going to be released whenever we break a chemical bond. That's what's kind of fun about chemistry. And that's why so many chemists, you know, what's the classic thing you think of with a chemist? You think about some scientist pouring stuff into a bottle, you know. You guys remember being in science class? My teacher set our football field on fire when I was in high school, trying to show us how like phosphorus works, you know. Well, whenever you break the bonds in something, a bunch of energy gets released, usually in the form of like heat. That's why it's explosions, and light, which are versions of energy. And what's funny is your body actually does that constantly. Your body is constantly breaking things down to release heat and light, and it captures that energy in order to do stuff. So if we were to literally just break down all the energy, let's say you go to McDonald's and you get a Big Mac, right? You go to McDonald's, you get a Big Mac, and that's got a lot of calories in it. It's got a lot of energy in that hamburger, right? If your body was able to break all that energy down in that hamburger instantly, you know what would happen? You would experience a small little explosion if it could do it instantly. Luckily, that's not how it works. It's kind of a slow process. And our body doesn't just capture direct energy. Instead, what our body captures is this high energy molecule called adenosine triphosphate, or more commonly referred to as ATP. So ATP is our version of energy, okay? And it looks kind of like this. It's this little molecule of adenosine and 3 phosphates. That's ATP, okay? Adenosine triphosphate. So we'll make a whole bunch of these molecules right here. And then what we do whenever we want to release a little bit of energy, let's say you start walking up a hill, you know, or you need to just kind of keep yourself alive, what your body will do is it will break this chemical bond and it pushes off that 3rd phosphate. And that releases a whole bunch of energy. And our body captures that energy in order to do stuff. It's what's keeping you alive right now. It's what's keeping me upright. It's what's allowing me to contract the muscles in my jaw to talk. Everything we do is by releasing the energy in ATP. So the reason you eat is so that you can make ATP. And you break ATP down in order to do stuff. And that's how this works. That's what this whole course is going to be about. We're going to be talking about how we as individuals make ATP, because we do it in a lot of really cool ways. And that is the process of what we call cellular respiration. Cellular respiration describes how our cells take in nutrients and spit out energy. I, you, everybody we know take in carbohydrates, proteins, and fats, and we turn it into this molecule right here, ATP. You know, we leave it attached like that, and then we break ATP whenever we need energy. We break it, we break it, we break it. And that releases a bunch of energy. Just like an atom bomb, you know? Split an atom in half, bunch of energy gets released, right? Same thing is true in your body, just much smaller. So there are 3 ways that we are going to make ATP when we say cellular respiration. We are going to make ATP in a process called glycolysis. This is the first thing that you're going to do, okay? So glycolysis is the process of making ATP from glucose molecules. So yesterday, my girlfriend and I were in San Francisco as we were driving back, and we stopped by Boudin's sourdough factory, Boudin Bakery. I'm sure you've probably seen this bread for sale in stores and stuff, right? So they make sourdough bread. And remember when the pandemic first broke out? It was like everybody on Facebook and Instagram was like talking about how to make bread. You know, it's like such a weird phenomenon. Like my social media feeds were nothing about like, I learned how to make sourdough bread. I'm stuck at home. It's like people were crazy. Has anybody in here ever made their own bread? Flour, water, maybe a little bit of sugar, and yeast, which are little enzymes. So yeast acts as the little enzymes to kick off the chemical reactions. And when you put flour and water together, that's a lot of carbohydrates. Those chemical reactions, those enzymes, they're actually bacteria, little critters, you know? And that bacteria eats and thrives and lives and poops just like every other creature on the planet. And what does it poop out? It poops out carbon dioxide, actually. The same thing that we breathe in and exhale, and creates a bunch of energy. And that's why when you look at sourdough bread, it gets these little bubbles in it. That's actually bacteria. Kind of a fun fact here. Those little bubbles, and you know, it ends up baking kind of like that with those little bubbles in it. That's actually from the bacteria in the bread pooping, making little carbon dioxide bubbles. And it's delicious. Sourdough bread's my favorite, you know? And that's why sourdough bread's kind of tangy, you know? Now, your body actually takes in, your cells take in glucose. Now, when you're making sourdough bread, actually, I'll look that up again. Notice how when they do this, look at this, they put it in a jar with a lid on. And what that does, that lid, is it allows all that bacteria to go through a process that we call fermentation. For the record, all of my people in this call right now who have worked out before, you have definitely experienced fermentation, whether you liked it or not. Has anybody in here ever left their protein shaker in the car for a couple days and forgotten about it? And then you come back and you open the lid, and it's like that scene out of Raiders of the Lost Ark when they open the Ark of the Covenant and everybody's faces melt. You're like, oh, God. That's fermentation. All the bacteria in what used to be your protein shake pooped out a lot of smelly stuff. And you almost made sourdough bread. Throw it away. They're $3. Go get a new one online. Says the guy who used to do everything in his. I used to boil them to get them back. Try to get the smell out of them. So that is very similar to what your cells do. So your cells are actually kind of swampy. All your cells, you know, we're squishy, right? For the most part. All your cells are actually filled with fluid. So when you put sugar, which is kind of like flour, into your cells and you leave it in this non-oxygen environment, what it does is that sugar ferments, kind of similar to sourdough bread, thanks to all of the enzymes and materials inside of every one of your cells. And that spits out a little bit of ATP. It spits out in response this little molecule here, which, by the way, sourdough bread, if you ever make it, it's actually a little warm. It's kind of funny. You leave it in there, put the jar on, leave the lid on, leave for a little bit. You open it up, you'd think it'd be room temperature. Same temperature as it's actually a little warmer. You put your hand over it, you'll feel a little bit of heat coming off. That's a bunch of energy being released from that sourdough bread. That's exactly what's happening in every one of your cells right now. Your body is spitting out a little bit of ATP thanks to glycolysis. Now, here's the thing. This is what we call an anaerobic process. It takes place in the fluid of our cells. You can't breathe underwater, right? There's no oxygen in there. So it's an anaerobic, an for opposite, aerobic for oxygen. This is a without oxygen process. So glycolysis will spit out 2 molecules of ATP for every 1 molecule of sugar. So if I brought 1 sugar molecule, I would get 2 ATP molecules. Okay, I'd end up with 2 of these. And that's cool, you know, that's a little bit of energy. Pretty good return, right? I give you $1, you give me $2 back, you know? Pretty good. But here's the thing, it's not quite enough. 2 is not very much. But what is great about this is that it goes really fast. But what's really cool about glycolysis is that it is often referred to as the lactic acid system. And the reason we call it the lactic acid system is because the other thing that happens in glycolysis is you get a byproduct. You know, when you're making something, you always end up with like leftovers, you know? You always end up like let's say you're boiling potatoes, you end up with that soap scum, you know, this scummy stuff at the top. It's a little byproduct of whatever it is you're making, right? You get the murky water whenever you boil a thing of noodles, you know, it's the byproduct, it's the leftovers, you know? Well, the leftovers, the byproduct of glycolysis is this material that we call lactic acid, which you guys are probably familiar with if you've ever walked up a hill or lifted a weight. You know, you're lifting weights and it starts to burn, right? You're like, ah, God, that's starting to burn, right? That's lactic acid production. So lactic acid is really cool because we can actually use lactic acid to produce energy, just like we used glucose to produce energy a minute ago. And we do that through these next 2 processes in cellular respiration. Remember, cellular respiration is how our cells take in food and spit out energy. The first part is glycolysis. We get a little bit of energy from glycolysis, but we mostly get a whole bunch of lactic acid. It actually doesn't start out as lactic acid. It actually starts out as what's known as a pyruvic acid, but because it's in a no oxygen environment, it ferments into lactic acid. So we usually just call it that. Now, lactic acid is going to add a new ingredient to the mix. Some oxygen is going to come into our cells, literally. Air. The reason you have to breathe is because it's going to go into your cells and it's going to combine with that lactic acid. And we're going to go through this really cool cycle called the citric acid cycle or the Krebs cycle. And this is an aerobic process because now it's using oxygen and it's going to produce even more ATP. Now, I said this is an oxygen environment. I said that all your cells are wet. So how do you have oxygen in the wet cell? You know, how do you have oxygen underwater? Well, that's why you got these really cool little things called the mitochondria. You guys might remember this from high school. So we look at this picture right here. This fluid, the little like beige area in the middle, that's the fluid of every one of our cells. We call it the cytoplasm. That's where glycolysis takes place in this no oxygen, wet, soupy environment. But then lactic acid moves into this little guy right here. This little pink, kind of looks like a potato bug looking thing. That's your mitochondria. So we got 4 mitochondria in this little cell right here. So lactic acid goes in there, and then oxygen works its way through the cell and goes in there as well. And this is like a little air bubble inside of your cells that acts as sort of a factory. And it goes through the Krebs cycle, uses all these little B vitamins and enzymes to turn that lactic acid into 2 more molecules of ATP and a little bit of these high energy molecules called NAD and FAD, NAD and FAD. So glucose went into our cell here in the fluid portion, and it became 2 molecules of ATP and a bunch of lactic acid. And then that lactic acid goes into this little pink critter right here called your mitochondria. A little bit of oxygen goes in there as well. And now that lactic acid became 2 more molecules of ATP, and it became a little bit of NAD and a little bit of FAD. And now it's going to go through the last part of cellular respiration, where it's going to go through what's called the electron transport chain. At the very end of the mitochondria, there's this little pump, and it's going to take the NAD and it's going to take the FAD. This is an aerobic process that uses used to produce ATP in the mitochondria that uses byproducts of the other parts of your metabolism. So the whole purpose of all this has been to make ATP, right? And we keep making other stuff. Like, you know, you give me glucose and I'm going to make ATP out of it. But first, I'm going to make lactic acid. And then you give me lactic acid. I'm going to make some ATP out of it. But first, I'm going to make some NAD and FAD. Well, when we get to the final part, the final tail end of the mitochondria, this little pump is going to take NAD and it's going to take FAD, and it is going to spit out 36 molecules of ATP. Crazy, right? From 1 molecule of glucose. So we took glucose. It became 2 molecules of ATP and lactic acid. Lactic acid goes in. It becomes 2 more molecules of ATP, and it becomes NAD and FAD. And then NAD and FAD become 36 molecules of ATP. And now we're finally done with that glucose molecule. All that's left is the carbon. So we brought in that oxygen from earlier and we burned up that carbohydrate. All that's left is the carbon. So you know what we're going to do? We're going to take the wreckage of those oxygen molecules. We're going to add the carbon to it, and we're going to end up with what is called carbon dioxide. Little piece of carbon and 2 oxygen molecules. And then our cell is going to spit it out. And it's going to work its way to our lungs, and we're going to go like this. And we're going to get rid of our carbon dioxide, just like those little bacteria did earlier in the sourdough bread. We don't poop it out. We breathe it out. But that is how you create energy. Now, obviously, I went through this pretty quick today. That was not exactly the most detailed breakdown in the world. For the next 12 days, we are going to be talking about how we produce energy. But basically, let's go through this one more time before I leave you guys today. So the citric acid cycle is going to use all these really cool little enzymes to break down things like carbohydrates and fats into a little bit of that NAD and FAD so that it can become way more energy later on, ATP, right? The whole reason we're doing all this is because we're trying to spit out ATP molecules. We got 2 from glycolysis. We got 2 from the Krebs cycle. We get 36 from the electron transport chain. So it kind of goes in that order, sort of. Really, it kind of all happens all at once, but it's way easier to understand if you think it happening step by step by step. And ATP is how we use energy, right? Again, I'm going to create this molecule so that I can break this 3rd phosphate off and release a whole bunch of energy. And then my cells are going to capture that energy, and that's going to allow me to, you know, do all my stuff. It's going to keep you alive. You run off of this energy. So you need to be able to produce lots and lots of ATP. You can do it through the citric acid cycle. You're going to do it through, and it looks like this, by the way. Look at how freaking complicated this is. Luckily, you guys don't have to have this all memorized. But glucose becomes pyruvates, becomes lactic acid, and it goes through the citric acid cycle. So look at all these crazy little enzymes. And there it is. There's where it spits off a little bit of ATP. That's where it becomes those 2 molecules of ATP. But it's got to keep going through the rest of the cycle so it can create NAD and FAD, because we got to have the electron transport chain next. All the electron, look at NAD and FAD, by the way. Notice how they got little plus signs next to them. You guys see that little plus sign right there? Those are the little, electrons, right? So they're all going to get squeezed together in that electron transport chain. So we squeeze them all together, and that's how we get the 36 molecules of ATP at the end. Your body is kind of, every one of your cells, your mitochondria in particular, they're kind of like the world's most effective recycling plant, right? Why do we recycle stuff? So we can take that plastic, break it back down, and use it to make new water bottles later, but it's not perfect. We end up wasting a lot of it. Your body, though, is great at recycling. Glucose becomes lactic acid and a little bit of ATP. It becomes ATP, but that lactic acid, that's a byproduct, right? That's the leftovers. Well, those leftovers are the ingredients for the citric acid cycle, for the Krebs cycle, right? And it creates more ATP, but it creates NAD and FAD as a byproduct. And then the electron transport chain uses that byproduct, right? My parents owned a pet store when I was growing up. And, I learned way more about dog food than I ever wanted to know working at that pet store. And, when they butcher a cow, you think about it, it's like, what do they use? They use it for steaks and hamburger meat and stuff like that, right? But you know what? Everything gets used, all of it. They use every scrap of it. The same thing is true when it comes to glucose. Your body will break it all down. The same thing is true of fat. Your body will break it all down. Now with proteins, your body actually can't synthesize energy from protein directly. What it'll actually do is it'll take protein and it'll rip its nitrogen skeleton out and throw that away. That is actually a byproduct that never gets used. And then the leftover carbon, hydrogen, and oxygen gets turned into glucose, and then it just goes through the regular old glycolysis process. So you can produce energy from protein as well, but your body tries not to. It's not very efficient. It likes carbohydrates and it likes fats. Those are the two most efficient ways to produce energy. It can do it from protein, but it really tries not to. We'll talk more about that later. So the last part is the electron transport chain, and this is what that looks like. Glucose, lactic acid, Krebs cycle, and then eventually it goes, there's all the NAD and FAD. There's all the little hydrogen ions from NAD and FAD. And they go through this little pump right here, and that's how we get 36 molecules of ATP. So very complicated stuff to hear about on your first day. Very complicated stuff. Joseph, Chris, and Edwin, first time hearing it, really. I mean, well, we talked about it last module briefly, but day one today, it's your intro day. That is what we are going to be talking about for the rest of this class. We got 12 days in this course. And by the end of it, it is my job to make sure that you guys have a pretty good understanding of how we produce that energy. Because here's the thing. There is different types of energy that you are going to need. You know what's really great about glycolysis? It produces very little energy, but it produces it super fast. The other stuff produces a lot of energy, but it produces it really slowly. And that's where intensity becomes really important to understand when it comes to lifting weights. Think about how many repetitions you can do when you're lifting really light, right? Lift very little weight, you can lift for a long time. You can produce a little bit of energy for a really long duration. That's your aerobic metabolism. But when you lift really heavy, you can produce a lot of energy really quickly, but you can't do it for very long. That's glycolysis. So there's a very big difference between cardio, lifting weights, and there's really a big difference between 5 reps, 10 reps, 15 reps, and 20 reps. And we'll be talking about how that all ties together over the next 12 days. Tomorrow, we're going to take a break from the metabolism stuff, and we're going to dive into nutrition, because we're going to get into what happens before any of those chemical reactions take place. We got to look at how we break down our ingredients to even make that energy. So that will be tomorrow's lesson. But today you learned a little bit about glycolysis and how that produces some energy, the citric acid cycle, how that produces energy, and the electron transport chain and how that produces energy. And all of those are happening. Those are breaking stuff down, right? So we call that a catabolic reaction. And then we build it up into a different molecule. That's what we call an anabolic reaction. So questions, comments, concerns. How are you all feeling today? I know it's a lot on your first day. It's complicated.
Yeah, good.
Feeling good though. Edwin, do you guys recognize Joseph and Chris and Emma? You guys recognize this from last mod? Briefly.
Yeah, like a little bit, like the ATP stuff and all that.
Yeah, we were talking about it on our cardio day. So,
yeah.
Simon, Alexia, Sochi is meant to be very circular. You know, like you saw the whole program as a big wheel. We're going to be, you know, if you're like, man, I don't feel like I absorbed all that. I feel like I need to know more. Guess what? We're going to talk about it over and over. We don't leave stuff around. A lot. This is the difference between our school and, you know, if you guys had gone, you know, I went to school into exercise science, right? I took so-and-so 101. I learned it and I was expected to remember it forever. And they never revisited it. They just referenced it. We don't really do that here. We're going to teach you stuff and then we're going to review it. And it's going to come back around over and over and over again, rather than teaching it once and then leaving it alone forever. It's all meant to be very circular. You got to get your sets in, you know? But that's about it for today, guys. My recommendation, please review the PowerPoints. You can find them on Canvas. You will get them in email later today. I'm actually going to kill the recording here real quick.